The dot product, sometimes called the scalar product. So you might see that used, but normally we just call it the dot product. So if we've got two different vectors, I suppose they don't have to be different, they can be the same, but I'll call the first one x1, y1, the second one x2, y2. The dot product, very easy, you just multiply the x values together, and you multiply the y values together, and you add them together. And that's why it's called a scalar product, because the answer will be a number, it won't be a vector. Now the dot's very important. Okay, so make that dot clear when you're doing the dot product. So if I want to do this one, as I say, we just multiply the x's together and we'll get 1 times 6, which is of course 6. Multiply the y's together, minus 7 times 4, negative 28, negative 22. We get a number, we get a scalar. Just some rules for manipulating the dot product. It doesn't matter the order. So that's what that first one's saying there, if you're multiplying by a scalar. So you could, if you wanted to, multiply one of the vectors by the scalar first, then do the dot product. Or, if you prefer, do the dot product first, then multiply that answer by the scalar. Doesn't matter. Works either way. It looks like it's just algebra and we're expanding parentheses out. And we sort of are. But we're not actually multiplying. We're applying the dot product. But the same rules apply. So when I expand that out, instead of saying A times U, I'm saying A dot product U. So it's a subtle difference, but really all those rules of algebra are still going to apply. Yeah, commutative, doesn't matter which way around you have it. U dot V will be the same as V dot U. U dot U, you could multiply it by itself, but look what happens. You'll end up with the x value squared plus the y value squared. Well, there's a neater way of writing that, because we saw that the square root of x1 squared plus y1 squared was the magnitude of the vector. So u dot u is the magnitude of the vector squared. And again, this is just illustrating the normal rules of algebra apply. It's sort of like the difference of two squares, but look what ends up happening with this one. Because we'll end up with u dot u minus v dot v, and we sort of do get the difference of two squares, but it's the difference of the magnitudes squared it ends up being. So here's our picture that we had for vectors. I've got v in there, u, and the red vector, head minus tail, so that's going to be u minus v. So I've got this triangle of 3 vectors, and I want to find the angle between u and v. I could use a cosine rule, it's still a triangle, but I've got to be careful what I'm squaring. I'm squaring the magnitude, I'm not squaring the vector, I'm squaring the magnitude. So the magnitude is the length, and that's the cosine rule, we use the length. So the red one, the length of that would be the magnitude of u minus v, whatever that is. So we'll square that. That's going to equal magnitude of u squared plus magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of theta. Remember, we're trying to find theta. Now I'm going to expand that out to get the x and the y values. You'll notice I didn't bother expanding out magnitude of u times magnitude of v. You'll see why when I finally compile it all together. So looking at the other ones, we actually have terms that are going to end up cancelling. Because on the left-hand side, if I was to expand out that x1 minus x2 squared, I'd get x1 squared minus 2x1 x2 plus y1 squared, but the x1 squared and the y1 squared would cancel with the x1 squared, y1 squared, which is on the right-hand side. So I'd be left with that expression there. But I get 2 times the dot product now is 2 magnitude of u, magnitude of v cos theta, because on the left-hand side, I did divide by the negatives. I've got x1, x2 plus y1, y2, which is the dot product of u dot v. So now there's another way of working out the dot product. It depends what information we have. So u dot v we could calculate by going magnitude of u times magnitude of v times the cosine of theta. But if it's the angle that we wanted to find, we'd make cos theta the subject of that and we could sub in the appropriate thing. So we've got our 2 vectors. We want to find the dot product. We now have 2 options, depending on the information that we have. Easiest way, if we have the x and the y values, brilliant. Multiply the x's, multiply the y's, add them together. If I've got the angle between the vectors, things like that, I can use the magnitude of u times the magnitude of v, cosine theta. That'll work. Theta in this will always be acute or obtuse. Okay, so we don't say negative angles for this one. It's either going to be acute or obtuse. Why? Well, look where it came from. It came from an angle inside a triangle. And angles in triangle are either going to be acute or obtuse. So let's find the angle between these two vectors then. Right, we said A dot B, magnitude of A, magnitude of B, times the cosine of theta. Rearrange it, make cos theta the subject. So it'll be A dot B over magnitude of A, magnitude of B. Okay, A dot B. Multiply the x values together. 3 times 4, that'll give me 12. Multiply the y values together. Minus 2 times 1, that'll give me minus 2. I have 10 in the numerator. Bottom of the fraction is the length of those vectors. 2 squared plus 3 squared. 2 squared plus 3 squared. 9 plus 4 is 13, so we have root 13 for the first one. And then the second vector, 4 squared plus 1 squared is 17, so we have root 17. 10 over the square root of 221. Now from there it's just calculator work. At 48 degrees. We tend to use degrees here. Maybe because we're talking about an angle in a triangle row. You could give your answer in radians if you wanted to. So consequences of our dot product. What are some of the things we can use this for? Here's a very useful thing. Proving vectors are perpendicular. Because if they're perpendicular, the angle between the vectors would be 90 degrees. And the cosine of 90 degrees is 0. So the dot product must end up being 0. So you get an answer with a dot product 0, you know, these vectors must be perpendicular. Or if they've told you it's perpendicular, you can say, well, that means the dot product must be 0. Works either way. Therefore, our special unit vectors that we saw must be equal to 0 when we dot product them. So I dot j and j dot I must be 0, because remember we set those up to be perpendicular. Parallel then, we can still use the same idea, because if they're parallel vectors, okay, they're not going to intersect, but their direction is going to be the same. So theoretically, if they were sitting on top of each other, the angle between those vectors would be 0. Cosine of 0 is 1. So if we end up with u dot v is equal to, could be plus or minus, but the magnitude of u times the magnitude of v, then we know those vectors are parallel. And it works the other way as well. If you know they're parallel, then you know u dot v will be the magnitudes multiplied together. I've said plus or minus on this. If it's positive, remember we're talking about parallel vectors. If they're positive, they must be going in the same direction. If it's negative, then they're going in opposite directions. And I dot I, j dot j has to equal 1. Remember they were unit vectors. And we said I dot I was the same as the magnitude of I squared. So 1 squared is 1. There's our theory for today.